In the early years of the ImageNet competition, the depth of the winning neural networks grew at a steady pace. We went from AlexNet's 8 layers to VGG's 19 layers. Then, in 2015, the depth of the winning architecture shot up to an astounding 152 layers. Researchers operated on the premise that stacking more layers allowed for the integration of increasingly complex, multi-level feature hierarchies. Depth was considered the primary driver of model capability. That massive 152-layer leap was introduced in a paper titled Deep Residual Learning for Image Recognition, written by Kaiming He, Shengyu Zhang, Xiaoqing Ren, and Jian Sun at Microsoft Research. But reaching 152 layers was not a simple matter of increasing compute. Whenever researchers tried to push models past roughly 30 layers, the network's accuracy would saturate and then aggressively crash. The immediate suspects were the gradients, vanishing into nothing or exploding out of control. But batch normalization and normalized initialization had largely addressed those issues. These deeper networks could start converging. They just couldn't improve. What researchers were seeing was a structural failure inside the optimization process itself, creating a mystery that simple scaling could not solve. This chart plots error rates during CIFAR-10 training. The lower lines show a 20-layer network. The higher lines show a 56-layer network performing significantly worse. Look at the training error on the left. The 56-layer network fails even on the exact data it's learning from. If the deep network were overfitting, its training error would be near zero, while its validation error spiked. Here, both errors are high. This is not overfitting. The researchers identified this as the degradation problem. Standard stochastic gradient descent solvers were proving incapable of optimizing standard nonlinear layers once the architecture reached extreme depths. Simply stacking convolutional layers was breaking the mathematical learning process. Scaling past 30 layers required an entirely different architectural paradigm. To understand why this degradation is a logical contradiction, we have to look at the theoretical capacity of these models. Here is our optimized 20-layer network. If we take this 20-layer model and add 36 additional layers on top, we can define those new layers as identity mappings. This means every new layer simply passes its input directly to its output without changing it. Mathematically, this constructed 56-layer model yields the exact same error rate as the original 20-layer model. It cannot perform worse because it contains the shallower model's entire solution within its own space. The degradation paradox exists because our solvers struggle to find this simple identity solution when optimizing multiple nonlinear layers from scratch. The challenge is to build a layer architecture that defaults to an identity mapping, allowing the network to easily learn nothing if no change is required to the signal. This is a standard neural network layer block. An input vector, x, flows into weight layers as the solver attempts to fit those weights to a desired underlying mapping, which we'll call h of x. The Microsoft team split the input. One path routes around the weight layers entirely, creating a parameter-free shortcut connection. Because the original input x is now bypassing the weight layers are no longer trying to learn the entire goal mapping.
Their output is now the difference between the input and the goal, a residual function, f of x. The two paths are recombined at the end via element-wise addition. The final output for the block is f of x plus x. Instead of forcing the layer stack to approximate the full mapping h of x, the architecture explicitly forces the layers to approximate only the residual, f of x equals h of x minus x. This preconditions the problem. If the optimal state for this block is an identity mapping, the solver simply drives the f of x weights towards 0, leaving only the original input x to pass through. The paper validated this by analyzing the standard deviations of layer responses. The learned residual functions consistently hovered near 0, meaning the networks were using the identity shortcuts as intended. Because the shortcut is a direct identity pass-through, it adds no parameters and zero computational complexity to the model. By reformulating the objective to focus on the residual, the network maintains its ability to learn as it scales to 152 layers, and even experimental models with over 1,000 layers. This comparison shows VGG19 on the left and the new ResNet structure on the right. You can see the rhythm of shortcut connections arching over every 2 convolutional layers. When feature map sizes change, these dotted shortcuts use one-by-one convolution projections to match dimensions, so the addition step can still occur. While the 34-layer ResNet was highly accurate, the team wanted to scale to 152 layers while keeping the computational cost manageable. For these ultra-deep models, they designed a bottleneck block. An input of 256 dimensions flows into 3 distinct layers, wrapped by the identity shortcut. The first one-by-one convolution compresses the 256-dimensional data down to 64 dimensions. This reduction saves massive computational time before the data reaches the more expensive 3x3 convolution layer. A final 1x1 convolution scales the data back up to 256 dimensions, restoring the vector so it can merge with the identity shortcut. This bottleneck architecture allowed a 152-layer ResNet to maintain a complexity of 11.3 billion floating-point operations. That is substantially lower than the 19.6 billion required for the much shallower 19-layer VGG network. The team submitted an ensemble of these 152-layer residual networks for the 2015 ImageNet competition. The model achieved an ensemble top 5 error rate of 3.57%, securing first place in the classification task. The researchers observed no degradation at 152 layers, proving that accuracy could scale effectively with network depth. The results from the 152-layer model proved that with the correct architectural design, performance can continue to scale with depth far beyond the 30-layer limit. The architecture immediately dominated various other computer vision domains, including ImageNet detection and the COCO object segmentation challenges. The concept of residual learning, the f of x plus x shortcut connection, quickly expanded beyond convolutional networks. Today, residual connections are a structural requirement for modern transformer architectures and state-of-the-art sequence models. He and his team provided the architectural logic that remains a structural requirement for the current generation of massively deep neural networks.